Hello and good afternoon, everybody. Sorry for that we are now just continuing, but I got last week on Wednesday got vaccinated, and then I was at first nearly 1 week sick. So and today it becomes now a little bit better, and now we are starting with the last chapter from our applied geochemistry class, and that is related to the formation of diamond ore deposits. So in this class I have much more picture to show, and the class will also take longer as usual. I think so. Maybe I have to continue with recording tomorrow as well, because there I have a lot of material, because I'm by myself very interested in diamonds, and it is one of my topics where I'm carrying out my own research. So here we have quite a lot of very nice, very well-shaped diamonds after the cutting and the polishing processes, yeah. So, and these the pictures from that diamonds in this presentation, you remember I have handed out you 2 PowerPoint presentations about the diamonds, and these pictures from the first presentation, they were done in the Letseng diamond mine in Lesotho, which is the highest diamond mine on the planet. It is above 3,200 meters above the sea level. So, and when you are, I don't know if you have ever visited diamond ore deposits or places where they have discovered diamonds, then the first diamonds, they were discovered in South Africa, in Kimberley, and there is nowadays the so-called Big Hole. There is a museum and everything there in this Big Hole. They have mined the diamonds there. There was the kimberlite pipe. So, and this huge necklet, which is hanging around the neck from the Queen of England, that was made from that diamond, from this particular Big Hole in Kimberley, and these diamonds were found in 1869. So here we have a map from Lesotho. Yeah, I told you these pictures are from Lesotho. So, and they have this diamond mine, the Letseng diamond mine, yeah, that is here. I mean, or I hope you know where Lesotho is. That is an island, forms an island in South Africa, and it is up to 3,200 meters above the sea level. Yeah, here we have the Thaba Putsoa, that is 3,096 meter high, and here we have the Tabana Netlandiana, that is even close to 3,500 meters above the sea level, and the Letseng diamond mine is about 3,200 meters above the sea level. Here on the lower right corner or left corner you have a scale, and you can see that Lesotho itself is not that big. And here you have then the Katse Dam, and at the Katse Dam there is a hydropower plant. So here we have Candice Swanepoel. She is a South African model. So, and she is very happy, like you can see on this picture, because she has a handful diamonds. And here we have then a 603 carat stone. And you know that 1 carat is 0.0 gram. Next slide. So we have here in Letseng, we have 2 kimberlite pipes. we have the main pipe, which is 17.2 hectares, and the satellite pipe, we have 5.2 hectares. That is in most of the diamond mines the case. You have there the different pipes, and you can have up to 50 pipes, which is fed by one kimberlite, yeah. So, but it must not be that all the kimberlites are diamond bearing. So they have a very important aspect, that is the quality. So, and in Lesotho we have an output of 75%, which we are calling gem diamonds, which have gem quality, yeah. That is actually a very good grade, because from the others you can only make sandpapers. So, and the size of the Lesotho diamonds, they are about 1 carat per stone. So, and here this one, which has a lot of inclusion inside, has already 171 carats. So, and here on the right hand we have a size frequency analysis, and then you can see the bigger size diamonds, they are much more rare compared to the small ones, yeah. So, and then we have the diamonds have different shapes. I will talk later on about the shapes, but here you have already a small pictures below. You have the octaedron, the dodecaedron, and the muckle. So, but the dominant size that is dominantly shaped, flattened, and an elongated dodecaeder, with a number of 20,696 stones. So here we have then two diagrams, these cake diagrams, and showing us in the satellite pipe we are getting 87% of all diamonds are dodecaedron. Then we have 12% are muckles and 1% is broken. So whereas when we are going to the main pipe, we have then 67% are dodecaedrons, 32% are muckles, then we have 0.9% which are broken stones, and we have 0.1% which are octaedrons. So most Letseng diamonds show a high degree of resorption. So, and that is actually a thing which we don't like as diamond miners. That is resorption. That is when parts of the diamonds becomes resorbed and this carbon goes back to graphite, yeah? So, and I mean for graphite you don't get money, and then you have such resorption effects. So now we have here this resorption that is caused by or supported by the resorption of other mantle-derived minerals and coarse kimberlite minerals. You know, diamonds brought to brought to the Earth's surface by a kimberlite. The kimberlite is just a transport mechanism. It has nothing to do with the formation of the diamond, but the kimberlite acts like a catalytic converter. So when this catalytic converter can be or is the cause of the resorption of the diamond. Because if our kimberlite has a too high oxygen fugacity, that means the oxygen fugacity within the kimberlitic melt is, if this is too high, then resorption will start. So, and when resorption starts, then our diamonds can, under certain circumstances, they will just react away. So here on the right, on the upper right picture, we have an olivine xenocryst with sawtooth texture, and you can see this sawtooth texture that is there where the red arrow goes, yeah. So and such as that is a typical resorption texture where the olivine crystals becomes affected. So and this resorption in olivine, I mean the olivine which you can find in a kimberlite, that is the so-called montichelite, which we will then talk also later in this class about. So then we have coarse and sometimes complex shaped olivine phenocrysts, like it is here in the picture below, and there you can't see any resorption. So that means the oxygen fugacity was then lower at this time. So then we have another thing. This is the color of the diamonds. Yeah, when you are going to a diamond store, you like to buy a diamond for your girlfriend, then most of the diamonds, they are white. So, but these are the normal diamonds, like you can see here in this picture below, but you have a lot of color varieties, and you have then the fancy diamonds, and they can be yellow, brown, gray, bored, and then really fancy colored like pinkish and such things, yeah. So and there that is then a thing of the price, yeah. So and therefore we have now in the satellite pipe 33% of white diamonds, 41% of yellow diamonds, 15% of brown diamonds, and 10.9% of gray and bored diamonds. And gray and bored diamonds, I mean nobody is buying a gray diamond. So and then you have this very small number of 0.1% of these really fancy diamonds. So when we are looking at the outcome of the main pipe, we have 32.5% white diamonds, 29% of yellow, 35% of brown diamonds, only 4.75% of the gray diamonds, but no, in fancy diamonds we have still 0.25%. So and then you can just assume it very easily. These fancy diamonds, they are then very expensive. Here below we have these pictures. We have the white diamonds and a lot of colored diamonds. Yeah, that is from the diamond table in the Letseng mine, because the Letseng mine is owned nowadays by Petra Diamonds or Gem Diamonds. I think it is even Gem Diamonds, and they have not these strong regulations like De Beers has. So and they are allowing you to go to the diamond table and watch the stones. So here we have such a fancy diamond. Yeah, they are then very, very beautiful, but you can see it's still a very, very small stone. So then we are distinguishing between different types of diamonds. Generally, we are distinguished between type 1 and type 2 diamonds, and that you can identify using a Raman spectrometer, because then you are getting the different peak shift. If you have high peaks at the wave number of 2000, then you are talking of a type 2A diamond. If the wave number is at around 1250 centimeter, then we are talking about a type 1 diamond at 2500. That is then another hump caused from a type 2 diamond, and that is then a method where we can fingerprint diamonds from different diamond mines. So we can then exactly say this diamond is a Namibian diamond, this diamond is an Angola diamond, and blah blah blah, because all these different diamonds from the different mines, that means from the different kimberlites, they have their own signature in the spectrometer. So then you can measure also the fluorescence like it is in the picture above, and then you have the visual signature as well, and you can then measure also the size of the diamonds. So here we have then the percentage of type 2 diamonds per size fraction in the satellite and in the main type, and they have for statistical reasons they have checked 22,572 stones. Yeah. So and in the Letseng mine we have the situation that you have more type 2 diamonds. I mean, here on the x-axis we have the weight in carat, yeah. So 10.8 carat, 5 to 10 carat, 2.4, 2 till 4 carat, 3.6 GRN, and that is very small. And then we have then the size which we are expecting from the sieve. So and in the Letseng mine they have by now found 27 stones which have which are bigger than 100 carats in a time slot between November 2003 and May 2009. So and from these 100 stones we had 63% white diamonds, 7.5% brown diamonds, and then we have 18.5% type 1 diamonds, and then just 11% bored. So then we have the 4C of the diamonds. I think you are coming from a diamond country, so then you should know the 4Cs of the diamonds. So here we have the cleavage, that is unnatural breakage on a 32 carat type 2A stone, and we have here in the small inset below at the corner on the right, we know the corner on the left, we have a stepped cleavage, yeah. So then we are dealing with the price of the per carat from 2004 to May 2009. That is not very actual, but then you can see that the diamond price is strongly dependent on the world economy, and in 2009 we had an economy crisis, and when we have an economy crisis like we have it nowadays as well, then the price per carat for per stone goes down. So now we have different stones here, nice stones which they found at Letseng, and how they are looking after the cutting and polishing processes. Yeah, we have here a 123 carat stone, and what is left, that is then the Star of Lesotho, which is a 53.11 carat. So then we have here on the right hand a 125 carat stone, and from this 125 carat stone they have produced the Sun King, which has then 40.06 carat. Then here on the lower right left hand we have the 603 carat Lesotho Promise, and from the 603 carat Lesotho Promise, they have produced a lot of single stones, which has then 76.41 carat, and this whole baggage consists of jewelry of 26 pieces. So, and then finally on the right lower hand, we have a 28 carat pinky brown stone, and we could produce 3 carat and 5 carat pear-shaped stones. So, and that is, I mean, most diamond mines are open pit mines, and here we have then a picture from the Letseng mine. These are just very big hole, but for you as a miner, it is then more comfortable to work in such an environment. So now we are continuing with our class here, yeah, that is that what I have put together, yeah. So at first I will start with a table. At first we have a list from the mines in the different countries. Then the surface area in hectares, then the approximate grade of carat per tons, then the percentage of gems, and then if they are related to kimberlites or lamproites, yeah. So the world's biggest mine in types of the surface area, that is the Madui mine in Tanzania, which is close to Lake Victoria. But we have here a smaller grade. It's about 20 to 25 carats per ton. And the gem quality, 40% of all the stones are of gem quality, and they brought up by kimberlite. So we will now not go through all the different mines in details. But the biggest diamond producer nowadays worldwide, that is in Botswana. I mean, Botswana is the biggest diamond producer. And the mine which produces most of the worldwide diamonds, that is the Chaneng mine, which is about 200 kilometers to the west of the city Gaborone. The surface area is 51 hectares, and you can see the approximate grade of carats per ton is 140. We have a gem quality of 50%. It brought up by a kimberlite. So then we have here, for example, South Africa, the world famous Roberts Victor mine. It's Eclogite. There you are producing E-type of diamonds, which I will also tell you later what an E-type and the P-type is. It's a small mine which has a surface area of 0.5 hectares. Approximate grade is also not that high, 27%. Gem quality we even don't know. And the diamonds have been brought up by a kimberlite. So now I will just spend 2 words on the Australian mine, the Argyle mine and the Ellendale mine. So these diamonds have not been brought to the surface by a kimberlite. It has been brought to the surface by a lamproite. So in the lamproite, this is also like a kimberlitic melt, but it is chemically different. So, and it is always related to orogenic belts, which is not the case when we are talking about kimberlites. Kimberlites are always cratonic. So we have here already this thing, major minerals, minor minerals, and xenocrystic minerals, yeah. So we have then here a list from the major minerals. So we can find the mineral olivine in both kimberlite and lamproite. We can find phlogopite in kimberlite and lamproite. We can find diopside in kimberlite and lamproite. But in the kimberlite, we can also find calcite, serpentine, and montichilite, which is a calcium-bearing olivine. So and compared to that, in the lamproite, we can then find leucite, amphibole, enstatite, and sanidine, which are not occur in a kimberlite. So then the minor minerals, in both of them, you have apatite, perovskite, ilmenite. Ilmenite is a very important indicator mineral for diamond exploration. We have spinel. So, but in the lamproite, we can have additionally priderite, nepheline, and vadite. So in the nepheline and the vadite and the leucite above, these are silica undersaturated feldspars. So then we have xenocrystic material inside, yeah, from the surrounding area, from the diamond window. There we have olivine, garnet, diopside, enstatite, and spinel. All of them occurs in both in the kimberlitic melt as well as in the lamproite. But the garnet is here also a very important indicator mineral in the diamond exploration. So then we have to distinguish between peridotitic diamonds, which we are calling P-type diamonds, and between eclogitic diamonds, which we are calling E-type diamonds. So here we have two diagrams. On the y-axis, we have the number of the analyses, and on the x-axis, we have in both diagrams the carbon isotopes. So now we can see that carbon isotopes in peridotitic diamonds ranging between 0 and -10 roughly. They are very homogeneous in peridotitic diamonds. So, and in eclogitic diamonds, they are varying, they are showing a huge variation, scattering between 0 and -30. So that means when we are comparing an E-type diamond with a P-type diamond, then both of the diamonds, they are formed by different carbon. So why is this? So I mean a peridotitic diamond occurs together with mantle xenolites of peridotitic composition. So, and these are then garnet lersolites, yeah? So they are coming up from the diamond window, and then they are coming to the Earth's surface together with the diamonds. So whereas when we are talking about eclogitic diamonds, then they are associated with eclogites, and they brought to the surface with eclogites. So in the peridotite, that is a rock which is formed in the Earth's mantle as well as the eclogite, but the peridotite and the related diamonds, they are affected by carbon released by the Earth's mantle. Yeah? So, and when we are looking at the history of an eclogite, then we know that an eclogite was formerly oceanic crust. So when this oceanic crust becomes subducted, I mean, that is the general or the most common way to produce an eclogite. There are also other methods around, but that is the most common way. So, and then this oceanic crust, these gabbros or basalts becoming subducted. At first, at the ocean floor, hydration will take place, and you will hydrate the basalt and the gabbros. And these gabbros and basalts, they are underlined by sediments. So, and in these sediments, you have a lot of shales, yeah, from biogenic activity at the ocean, yeah, and when these shales are dying, then they become sedimentated on the ocean floor. become also subducted together with these gabbros and peridotites. And from these gabbros and peridotites, we are making in the Earth's mantle then an eclogite. And from this carbon, from this shale, we are making then diamonds. So, and therefore the E-type of diamonds showing a completely different carbon isotopic pattern as the P-type of diamonds. So, and here we have, for example, for comparison, a histogram of the isotopic composition of the bulk carbon in carbon aqueous chondrites. You know, in meteorites. So, but for us more important, we have here graphite in ancient metasediments at amphibolite grade. And then you can see you have also this huge variety in carbon and metasediments. In these metasediments you have then also your metamorphosed shales inside. So, and here number B, we have the eclogitic diamond. We have here data from the Sloan group in Canada and the Robert Victor group in South Africa. And then you can see here you have again this huge scattering. So, and when we are comparing this isotopic composition in the graphite from the ancient metasediments at amphibolite phase grade, then it is comparable with those ones from our eclogitic diamonds. So here we have a PT diagram from the Finsch diamond mine in South Africa. So here we have the peridotite solidus. I will make it a little bit bigger, then one can see it better. So here we have the peridotite solidus. Here we have the PT conditions under which the Finsch peridotite is formed. And here we have the geotherm. Not the, the geotherm, and here we have the graphite diamond boundary. So, and here within this, that is the shield geotherm, yeah, and here between 40 milliwatt per square meter and 50 milliwatt per square meter, which is ideal for the diamond formation. And our peridotites from the Finsch mine lying exactly inside, and but they are out of the diamond window here in this picture. So, but you can see we are dealing here with temperatures of about 1000 degrees, and we are dealing with pressures of 40 kilobars, which is then a little about 130 kilometers. And we are still not in the diamond window, which I will show you then later. Here it is again. Yes. Here we have a picture, PT diagram from the McGregor mine, also in, I think, that is in Canada. So here we have again this dry peridotite solidus. That means when melting in the solidus occurs under dry composition or dry conditions. And here we have the curve from the solidus at vapor saturated condition. Here we have the xenolite field, that is where chemically all the xenolites are plotting. Then we have here the adiabatic decompression. Yeah, we have to bring the diamonds very fast back to the surface, otherwise they becoming resorbed. Here we have the shield geotherm again, yeah, that is also very good. And here the boundary between the graphite and the diamonds. So, and we are lying here very perfectly inside and fulfilling the conditions for the formation of diamonds. So therefore, and that is now to construct all these phase diagrams, that is all pure petrology, but it is in exploration very, very helpful and very important, because we can do with a minimum of financial support, we can get a lot of necessary datas. Here again, the thing with the geothermal gradients, we have here 45 milliwatt per square meter, 40, 35 and estimated. So, and we have here lersolithic garnets and harzburgitic calcium garnets. So I hope you know or remember still what an lersolite is and what an harzburgite is. So here we have the pressure. Here we have again the graphite diamond boundary. Here we have the temperature and all our mineral assemblages from the calcium-rich garnets, plotting here in the diamond field, and also some of the lersolithic garnets. So, and we are looking therefore at a special chemical composition of garnets, which are formed under the same pressure conditions and temperature conditions like the diamonds, and therefore the garnets are good indicator minerals, and you can find them very easily on the Earth's surface or in the kimberlite, because they are very you can see them very easy because of their red color. So, and there we are looking for a certain garnet composition, and that is then the composition of a G9, G10 garnet, which I will show you then later. So here we have two pictures from South African diamonds, I think so, because we have here the Indian Ocean, the Atlantic, Indian Ocean, Atlantic, two models, yeah. Here we have the lithosphere above, yeah, in both cases. Then you have here the boundary between the lithosphere and the asthenosphere, and here you have the graphite diamond boundaries. So, and then here the same, but here we have another, the boundary between the lithosphere and the asthenosphere is different, as well as those ones from the garnet and the graphite. So, but it is clear here we are dealing with the diamond window, and the diamond window is somewhere between, in a depth of about 100, let us say 150 to 225 kilometers. There we have the pressure and the temperature conditions where we can form diamonds. When we are going to this picture here, we can form them even in a depth of 250 kilometers, something like this, yeah? So then all these diamonds sitting here around, beneath the boundary of the lithosphere and the asthenosphere. So, but then finally you have to bring them up to the Earth's surface, yeah, because we do not have any possibility to go there. So now we have to bring them up to the surface, and therefore we need in most of the places around the world a kimberlite. or in Australia, the lamproite. So when this kimberlite is just going through, it's just going through, and if there is a diamond on its way, then it brings the diamond up to the surface. If the kimberlite goes through here and there is no diamond around, then the kimberlite cannot pick up anything. So then the kimberlite has to be of a certain composition in terms of water concentration, CO2 concentration, and oxygen fugacity, because otherwise the diamond will become resorbed. So when this kimberlite has to be very fast on its way, because after 20 minutes the diamond will start to resorb. So, and if you like to pick up at the Earth's surface a non-resorbed diamonds, then you must bring them through from the diamond window to the Earth's surface within 10 minutes, yeah. And therefore you need, from this depth, you need about 330 meters per second, and 330 meters per second, that is 800 kilometers per hour, and that is the speed of a jumbo jet. So that is so far to the description from the diamonds, from the diamond window to the Earth's surface, and where they are formed. So then they can form in the asthenosphere, that is here, yeah, diamond-bearing asthenosphere. And then we have diamond-bearing garnet harzbogites. They are then more in this field, yeah. Then we have here barren kimberlites, and here we have diamond-bearing kimberlites in Model B. Here we have another nice picture. I have written down always the source where I have these pictures from, yeah. So I mean, we have at first the formation of a depleted continental lithosphere like it is here. The boundary between the lithosphere here and the asthenosphere is in the depth of 100 kilometers. So then, and it is very thick, the root goes down up to 300 kilometers here, yeah. So then we have thermal erosion of the continental lithosphere and preservation of diamonds above the mechanical boundary layer. And the chemical boundary layer, the mechanical boundary layer is here, and here you have the graphite diamond boundary. So, and here TBL, we have here the thermal erosion, and that is caused by the convective mantle, yeah. So, and then we have the emplacement of a so-called megalite. And the megalite, that is just a fragment of an old subducted oceanic lithosphere, yeah? And this old subducted oceanic lithosphere, it's just hanging around in the mantle because the crust above is moving, but the mantle is stationary, yeah? So, and that is like the situation in South Africa. You have there everywhere these old subducting slabs hanging around, and these slabs, you know how they are formed or how they are made up. You have at the top everywhere these very hydrated sediments, and beneath the oceanic crust and blah blah blah. So, and then you have the release, because the megalite is sinking down, then you have the release of all these volatiles within the oceanic crust, and then you are forming the kimberlitic melt. So yes, and this kimberlitic melt is a potassium-rich melt, and the potassium you have in these sediments lying above. So, and this kimberlitic melt has a very low viscosity, is actually like gas. So, and then this melt is shooting up and picking up the diamonds. If there is a diamond on its way. So I mean these kimberlites, the fact that they are going very fast through the Earth's mantle, then they need a pathway. So, and one explanation is they are using former volcanic vents. But you do not have everywhere volcanic vents. So, but another explanation is, and this explanation I personally prefer because I'm working on that, that is the movement of crack formation. So, and the movement of crack formation, that is like, you have this at a few places on the Earth, and the most famous place where you can see the movement of cracks, that is in avalanches. I mean, you in Namibia, you have nowadays no avalanches because they are now gone since a couple of 100 million years. I mean, the glaciers, yeah. So, but when you are going to the North Pole, or I mean to the Arctic area or to the Antarctica, there you have a lot of glaciers, yeah. So, and I mean, in these glaciers, you have a lot of cracks inside in the ice, and these cracks are very deep. So, and within the cracks, you have water. So, and when such a crack starts to move, then they are moving very fast. They are moving very fast. They are opening and closing, and these cracks are very thin, yeah. They are not, in diameter, they do not have than 1 meter or so. So, and then the water becomes just within seconds pumped through. So, and that is the thing what I'm personally thinking, there is a good opportunity, but there has still a lot of studies to be undertaken to understand this formation of crack propagation. So here we have now another nice picture from Canada. We have here the Hudsonian orogen, the superior. So how it looks like below. We have here the asthenospheric mantle, and this asthenospheric mantle is overlain by the lithospheric mantle. And we have the graphite diamond boundary, the isograde, and we have here the zone of kimberlite magma generation, and these are Cretaceous kimberlites. So when they are just rising then up, because they have such a low viscosity, and then they are just rising up, taking everything what is in its way. And if they are going here through, and there are some diamonds around, then they are going like a rocket through the lithosphere and bringing the diamonds up to the Earth's surface. So here we have a nice schematic map, which I like personally very much. So we have here a typical subduction zone. We have here the craton, yeah. Then we have here the mobile belt, yeah. So here we have the subducted oceanic slab, yeah. So, and here we have fragments of the slab hanging around. These are flat subduction zones. And here we have then the places where the different diamonds are formed. So, I mean, these diamonds within the eclogitic slab, they are related to eclogites. These are then the E-type diamonds, yeah. So these are this one, subducted eclogite, and therefore you are forming then the E-type diamonds, this one here, yeah? So then you have here the garnet harzburgite diamonds, these are P-type diamonds, yeah? You can have in one mine both types of diamonds. You can have E-type diamonds and P-type diamonds, yeah? I mean, if the kimberlite comes here up from the Earth, from the asthenosphere, here it's a kimberlite type 1. We will discuss this also later. We have two types of kimberlites. The kimberlite type 1, that is monticellite serpentine kimberlite, and the kimberlite 2, that is the orangenite, and the orangenite you can only find in different areas in South Africa, around Kimberley. And they, the type 2 kimberlites, they are formed in the boundary on the asthenosphere lithosphere. So, and therefore they are very mica rich because you have a lot of material and contamination from the lithosphere inside. So, but that is so far to the kimberlite, later on a little bit more. So, and if the kimberlitic melt goes here through, here are some diamonds around, then the kimberlite will just bring them up to the surface. You can sample them here. When the kimberlite goes through here, there is no diamond around, then in kimberlite pipe K4 you will not form a diamond. So, but here we have an L, because here we are bringing a P-type diamond here up to the surface, but we are going here through the mobile belt. That means we are dealing then not with a kimberlite, we are dealing with a lamproite. So, and that is the different things. Here we have also lithospheric eclogites. I told you at the beginning, not all eclogites are formed by subduction. We can also form some of them in the lithosphere, but the general thing is we are forming them by subduction. So this one we don't need. This one as well. This one as well. This one as well. Here, that one we need. That is now a very important picture from the use of garnets in diamond exploration. Because garnets are lying around on the ground and you can identify them very easily. You have a lot of them and they are reddish in the sand. So, and then we have here the G10, G9 garnet. We have here on the x-axis the calcium oxide percentage, and on the y-axis the chromium oxide percentage. So when we have then plotted the chromium oxide against the calcium oxide percentage, weight percentage from peridotitic diamond inclusion from garnet worldwide locality. So, and here we have the line between the G10 garnets and the G9 garnets, and this model was based from Gurney in 1984. And garnets with diamonds, they are plotting in the G10 diamond field, yeah. So you are looking chemically for such a garnet which plots here, in this field, yeah. That is the field for the G10 garnets. So, and then you have the first indicator that you can maybe find some diamonds as well, because these garnets are formed under the same pressure and temperature conditions as the diamonds in the Earth's mantle. It could be, but it must not be, yeah? So, and that is now the typical histogram plots. like such peridotitic garnets have to look like. You have here the number of the garnets on the y-axis, then ABC, and that is then just the calcium oxide concentration. So, and then on the next diagram we have the XMG. So, and the XMG for this typical peridotitic garnets which occur with diamonds, that it has then a ranging in XMG between 86 and 91, and a few of them even between 93 and 94. That means they are very rich in magnesium and poor in iron. So, and here we have then a bigger scatter in weight percent in chromium oxide, ranging between 5 and 15%. And then if your garnets falling chemically within these areas here, then you know these garnets have been formed under the same pressure and temperature conditions like or it would be possible to look or to do a further work on the exploration of diamonds. Here again we have this quadrilateral diagram, magnesium, iron, calcium at the corners, yeah. So, and now we have the symbols here. We have a number A. These are garnets from eclogitic diamonds, yeah, of course they are different, yeah. Then we have garnet from websterite xenolites. These are these triangles. We have eclogitic inclusion in diamond, that is the field D. I mean, that is then very promising if you have such a thing. Then the roundish balls here are concentrate of xenocrysts, and in the field A, that is here, that is unshaded area is the field of group A inclusions in diamond. Black field C, figure 4b. Then let us just check if we have a figure 4b. Here we have figure 4b. We have here the whole diagram again with all this concentration of the garnets. And here we have the shaded field of diamond inclusion defined by published analysis from Lawless in 1974, and that is this field, yeah. So, and that is the chemistry, how from that diamonds, how they are the variation in chemical composition of diamonds from diamond-bearing kimberlites. So, but then I told you also the thing about the ilmenite. If you have now identified diamonds in the field and measured them with microprobe to do this calculation, and you discovered that these garnets are possible, the first indicator for a diamond deposit, then you are going to the next step, you are looking for the ilmenites. So why is the ilmenite so important? So because you can have the iron titanium oxide ilmenite, and you can have the magnesium titanium oxide ilmenite, and then you have here Fe2O3, and this Fe2O3, that is iron 3+. So what is now the problem? When you have a lot of iron 3+ in your ilmenite, then the oxygen fugacity was very high, and when you are dealing with a high oxygen fugacity in your kimberlitic melt, then the diamond becomes resorbed. That is it. So we are looking now in diamond exploration for a magnesium-rich kimberlite. I mean, they have all a little bit iron inside because here they are just the end members. But this iron in the magnesium-rich ilmenite should be iron 2+. So what you don't need in your ilmenite in diamond exploration is iron 3+, because you are increasing the oxygen fugacity in your kimberlitic melt. So and when you are increasing the oxygen fugacity in your kimberlitic melt, then your kimberlitic melt is then also automatically more rich in water. So and when you have a more water-rich kimberlitic melt, then you are dealing, or the next thing which will happen is that your kimberlitic melt becomes a higher viscosity. Then the kimberlitic melt is not that fast, so and then it will not manage it in a proper time to rise up from the Earth's mantle to the surface, so that the diamonds can be preserved. That is the cycle, yeah? So here we are comparing now the strontium isotopes with the epsilon neodymium and the epsilon neodymium isotopes with different locations. So here at the top, we have here MORB. MORB, that is the ratio here in this field between the strontium 87 to strontium 86 isotopes plotted against 143 neodymium to 144 neodymium. And that is the isotopic composition from MORB, and that is the Middle Ocean ridge basalt. So, and here we have then also the ocean island basalt, and this small thing is MORB, this bigger thing is ocean island basalt, and that is kimberlite group 1, which makes sense because kimberlite group 1 is also produced in the asthenosphere like the ocean island basalt. So then we have here kimberlite group 2, and here between we have the potassic volcanics. Here you have kimberlite group 2, that is the orangenite, like you can find it in South Africa, which is a mica kimberlite, and this one is a serpentine montichelite kimberlite. Here you have a wide variety of isotopic composition with the Australian kimberlites, and here the south ones of Spain. So, and this dot, now we have to find here this dot, putting here the dot, that is then the composition of the bulk Earth. So, and bulk Earth plots exactly in the kimberlite group 1 field. So then we have here the Lewisite hills, yeah, these are some volcanics, and the Smoky Body, that is also some volcanic stuff. So, but here, especially for you, here you can then compare chemically kimberlite number 1 or group 1 with kimberlite group 2, and then you can compare them with OIP, with the bulk Earth, and with the MORB. So, and when you are looking here for kimberlite pipes, then you are going to that area, I forgot the name, it's Goisip or so, that is just in the south of Mariendal, and there you can find a lot of kimberlites. I do not know if they have done their exploration, but I know some old German guys in Namibia, and they did have all these documents where they have done 100 years ago exploration on diamonds. I mean, here in Namibia, they are sucking up the diamonds from the ocean floor, but before they were brought up to the Earth's surface by kimberlites, group 1 kimberlites most probably, and then such a kimberlite is very water sensitive. So if a kimberlite comes in contact with water, from a river or something like this, it becomes just washed out, and then everything becomes deposited in the ocean, and that is where Depth Marine is working and sucking them up from the ground. So this one we don't need. There we have then, this one we don't need. Yes, here that is more interesting for you guys. Here we have the kimberlites, that's an old map with Southwest Africa, So here we have the kimberlites that is in the Goisip area. You can see there are a number of kimberlites around, and here that is here in the top. At this time when they produced the map, they had in Botswana only the Orapa mine, Then you have in Rhodesia, that is today Zimbabwe, I think so. So, and here in South Africa, you have a lot of them. You have the Roberts Victor, you have the Premier mine, which is nowadays the Cullinan mine. So the Wesselton, the Lesotho mines, which I showed you, the Monastery, and. So there are a lot of mines around. So, but also in Namibia, there are a lot of mines around, and I would be very interested to work on them. So that is now how the situation looks in Australia. We have here the Kimberley block. Do not change it or getting confused with Kimberley in South Africa. Kimberley in South Africa is something completely different from the Kimberley block in Australia. There is an Archean block. So, and there you have then those diamond ore deposits hosted within the Archean craton. They are produced. The diamonds have been brought up to the surface by a kimberlite eruption, whereas the south ones in the mobile belt, in the surrounding mobile belt, that is the Leopold mobile belt here, has been brought up by lamproites. So in such lamproites, they have much more water inside. So, and therefore they have then a higher oxygen fugacity, and therefore they are a little bit slower on the road compared to the kimberlite. And therefore Australian diamonds are more resorbed compared to South African or Botswana diamonds. So here we have now such a kimberlite pipe, that is just the model from such a pipe. Here we have the different fascias, the diagram fascias. Then we have here silts. And here we have also stocks and silts, and I have a much more better picture. And that is this one, because on this picture one can identify the things. So we have here the diatreme related dikes, and these is maybe just such a crack propagation here as well. Then you have here a root zone, and here you have the diatreme fascias. You have a sill complex, that is the horizontal, whereas the dikes, they are vertical, as it is. So, and in the diatreme fascias, your kimberlite becomes then more and more explosive. So, and then you are forming at the top then around such a kimberlite pipe a tuff ring. So, but you are not forming such a caldera around like in a volcanic eruption. So why does this kimberlite becomes then at the last stage so explosive? There's also an easygoing thing. Such a kimberlite is very rich in volatiles, and these volatiles are water and CO2. So, and the mineral which crystallizes during the uplift and sucking out the water of the system. That is the serpentine, yeah. I mean, in this group 1 kimberlites, you have a lot of serpentine inside. So, and therefore, relative to that, your kimberlitic melt becomes very enriched in CO2. So, and this CO2 is a gas, and then it makes at the end poof, yeah. So, and therefore, you can then find these crater fascias with pyroclastics, with epiclastics, and so on. So, and then you can mine these kimberlites, yeah, like I have shown you in the Lesotho presentation. You can drive in with trucks, load the trucks and driving out in a classical situation. But here in, as far as I know, here in Namibia, they are not doing open pit mining because Steps Marine is sucking them up from the ground, because it seems that this is more promising. So that we don't need. Here we have something of the shape of the diamonds, yeah. We have then sharp-edged octaedrons, Excalibur kimberlite pipe, step-layered octaedrons from Russia kimberlite pipe. Then we have step-layered octaedron from Ellendale. So these are just the different shapes of the different diamonds. Just go through. And here the same, yeah. Here you have, for example, number D, a very nice cube. Yes, cube with edge pits. So here you have a nice octaedron with corrosion. That is how the raw diamonds then look like. Here you have also again another nice cube with rounded edges, yeah. Here you have a twin. And here you have just an octaedral aggregate. So now we have here different phase diagrams which are very important in diamond exploration, and these phase diagrams, these are the logarithmic oxygen fugacity temperature diagrams, and you can see how the influence of the oxygen fugacity at a given pressure and at a given XCO2. So how the diamond graphite boundary then moves. So I mean, here we have then the diamond graphite boundary at 1700 degrees Celsius. So, and here it is then already at 900 degrees Celsius. And that is then by the composition of your kimberlite. So, and there different reactions will take place, which will influence the oxygen fugacity. And the oxygen fugacity, that is the main key player in diamond preservation. That we don't need. We don't need, because that is then all too much. That is then more something for economic geology. Where are the carats per ton? So that is for our purpose better. Again, static composition 8 gigapascal, it's 80,000 bar. 80 kilobars, an XCO2 of 0.1, and the graphite diamond boundary, here the diamond producing field takes place at higher than 1600 degrees Celsius. So, but then the next important thing is that you have to bring your diamonds very fast to the Earth's surface. That we don't need. Yeah, this is the same diagram as before, yeah. Just watch it again, but there is no new information. That is just that exactly the same like I have shown you before. So now we have here this diagram. There, in the diamond business, there are a lot of fake diamonds around, yeah. So, but they are all not that hard like a diamond, and they are they do not have this wonderful color play. All of them, this wonderful color play when you are putting a diamond on your finger and the sun shines in, then you can see how the diamond reflects all the light, this light in different colors, in blue, green, yellow, and so on. And this wonderful color play cannot be seen in all the fake diamonds. So, but here I have just a list from fake diamonds, what they are using. Another very nice scientific thing is the total nitrogen concentration in diamonds, because that is also one of my main research things, which I started recently. You can measure with a synchrotron-based FTIR that has a very high resolution. You can detect nitrogen, small amounts of nitrogen in the diamonds. So, and this allows you then also to identify if this is a type 1 diamond or a type 2 diamond, and you can calculate from the diamond concentrations, just a few ppm. You can then calculate the remaining time, how long this microdiamond was in the Earth's mantle at a certain temperature, yeah. Because these microdiamonds, they are also very interesting because we are thinking that these microdiamonds are just formed shortly before the uplift or during the uplift. You know, at this time when the kimberlite has picked up them in the diamond window. So here you have again the nitrogen concentration from different diamond, but I have told you right now for what we are measuring, the nitrogen concentration of diamonds. That is a scientific play, but that is very important to do this, because that tells you the history, how everything is formed. Yes, here some diagrams more to that. So that is now everything to these 4 chapters which I have loaded up. And you are writing by the end of next week. Then that is time enough for the preparation. You can then just go through all this presentation and go through all the PowerPoints or these PDFs which I have handed out. Then read please the summary things what I have handed out to you, and listen to every movie which I have uploaded, maybe 2 times. That should be enough. because the questions which I have, they are strong related to that, what I'm telling you here. Okay, I will now upload the movie by